Alejo García from Uruguay, but currently in São Paulo.
Thank you. I must erase this before starting. We can do it both. Do I have two of them? No, I can. Okay. Acá hay otra. Is this okay? Forward, back. Perfect. Thank you. Obrigado. Obrigado. Okay. Okay, so thank you very much for the invitation. We are going to talk about fully chaotic models for higher genus surface homeomorphisms. So let me start like this. How do we study complicated objects? Okay, when you do math, most of the time you have something you need to understand and you don't. Okay, so when you look at that thing and you don't understand it, what you do sometimes, you make simpler models, okay? So you make toy models of your complicated stuff. For example, let's say a good example of this would be you have a flow, you have a fixed point, then you take the differential, okay? And if the differential is hyperbolic, then you recover a lot of information from the original system. So the idea is, which kind of models can I build such that they are simple, but also I can recover information from them, okay? So when we do not fully understand, blah, 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 try to compare to simpler models, okay? We still capture behavior from the original one. Okay, so in our context, a model will be a semiconjugacy. So you have your favorite dynamical system here, acting on X, and you have a surjective function such that it makes the diagram commute, okay? And you can do lots of things which are not useful. For example, you can take your favorite dynamical system and make a semiconjugacy to the trivial system. You send everything to a point and you do not recover everything, or you send everything to everything and it is as complex as before, okay? So what about in the middle? What is it that you can do, okay? Okay, the dynamics on an extension, I will say, I will say that these guys are factors of these guys, which are extensions of these, okay? So information is lost, as we were saying, when we try to control the coarseness of the semiconjugacy. We then try to control the coarseness of the semiconjugacy so that G, the factor, reflects some behavior of the original system. So let me give you some two examples in surfaces. Okay, so surface dynamics. A really classical one is a torus homomorphism in the isotopic class of a linear Nosov map. So I will take the example from Santiago to 111. Is an extension of it. So what we are saying is in that class, the linear model, which is very well understood, is a good model for any system which acts the same in the homology. You have something horrible, and then here downstairs, you have your 2111. Okay, so dynamics here are at least as complex as here. Okay, for example, you have all the topological entropy you want, you have your periodic orbits, and so on. Bam. The quotient space by the semiconjugacy is the same as before, but the fibers may be totally disconnected. Okay, so you have a point here, and you ask what are the perimages, and it will be a Cantor set, typically. Okay, so, or anything. You do not know. I mean, you do, but they suck. So another example, André G. Carvalho and Miguel Paternain prove that C1 plus alpha, so they use Pessin theory, diffeomorphism of a closed surface. So SG, you know, like genus G, no punctures, is an extension of a tight homeomorphism. Tight meaning every continuum carries positive entropy. So the idea is, if I have a continuum up here, where the dynamics carries no entropy, then I collapse it. That's the idea. So in the quotients, every non-trivial continuum carries positive entropy. So the disadvantage here is that the quotient space is not a surface anymore. It's a cactoid. Okay, so it has, maybe it looks something like this. It has some blobs, some sticks, and some more blobs. So the fibers look nice because they are connected, but the quotient space, not so much. Okay? So what is the example? What is the thing I'm trying to model? It's basically this. So the Cherenkov-Taylor standard map. Okay? I will not get into the formula for this. I just want you to get a picture of it. Okay? So it appears as the return map of the periodically kick rotator, you know, Poincare style. You have a differential equation. You take a return map when you have a surface through which every orbits go through. And for different, depending on the size of the kick, you will see something like that or something like that. I mean, this is a family depending on one parameter. But what I want you to see there is that there are essentially two different behaviors. You have some blobs and some fuzzy thing, okay? So different stuff. So you have your blobs. And in the middle, you have something like this. Okay? And the idea is to try to understand the dynamics, the topology of those things, more or less something like that. Okay? So this, for me, would be a complicated object, at least for me. So I will generalize a little bit this thing. The other map was not in the isotopic class of the identity, but we can easily modify it. So let me assume that we are on the isotopic class of the identity. Then I wrote non-wandering. You can assume area preserving if you like. Symplectic, it's okay. Non-wandering is only the topological version of that. And I will assume that the rotation set of my function has an empty interior. So just give me one slide to get, if you do not know that notion, it will appear. So let me state some things. Andrés Koropecki and Fabio Tau, they proved that for any such homomorphism, the dynamics look like that. Okay, it look like islands and sea. Okay, so you have your inessential set, which is a union of periodic disks, which in KAM theory are known as elliptic islands. Okay, and on the other hand, we have the essential set, which is a fully essential, meaning you have all the fundamental group, you know, all the pi1 codified in that set, which contains all the rotational information. Okay, meaning that for every, meaning that all the rotational information. This is known as the chaotic C. So some questions, okay, topological metric dynamical questions. How does this dynamic look like? Is the Lebesgue measure of the essential set greater than 0? Does it have an empty interior, okay? So sometimes people look at the images and say it obviously has an empty interior, but no, it is a simulation. What about the small scale? Do you have small islands everywhere? I don't know. Is the set of periodic points dense in the chaotic C? This is conjectured to be true, I would say. But we haven't been able to address this question completely. What about the size of the islands? Can they be as big as they want? Do you have some sort of thin and long islands, or are they uniformly bounded? So we will more or less address the two last questions, okay? Just more or less. Any questions up to now? Okay? So now a little bit of rotation theory, okay? If you have never seen anything like torus rotation theory, let's go. So I want to understand how orbits loop around my surface. Okay, you might as well know the rotation number for circle homeomorphisms. You know, every circle homomorphism has a well-defined rotation number, and every point has the same rotation number, because in the circle you have a well-defined notion of order. You know, so you have x, you have y, and you can say, oh, y is in front of x, but it is behind x plus 1. So x pushes y, and y pushes x plus 1, and blah. Okay, but in the torus, in surfaces, you do not have that. So let me start easy. If you have a periodic orbit, so you have a homomorphism, you take a lift toward 2. Okay, you take a lift to detect the loops. If you have a periodic point, you can define the rotation vector of a periodic point as the average movement. Let me add a drawing here. So imagine that you have, it's like this. So you have your periodic point of period 3. And what is the rotation vector of that periodic orbit? So you have basically you have to count how many times I cross the horizontal red line and how many times I cross the vertical red line with sign. Okay, so the algebraic intersection. So in this case, when I start, I go through the red line, the horizontal one, I go once, then twice, then thrice, and then I go back once, so it is 2. In 3 iterates, so 2/3, and in the other direction is 1/3. Okay, is that okay? Okay, but what do I do with non-periodic orbits? Okay, how do I generalize non-periodic orbits? I will go through an ergodic approach. Okay, so an ergodic measure is basically the generalization of a periodic orbit, nothing more. Okay, so same basis. For any point in the surface, I will define its displacement as the difference in R2. So basically, it's displacement. You know, you have R2, you have z hat, and you iterate. This vector is a displacement, okay? And then I will say that for any f invariance or f ergodic measure, I can define its average rotation as the integral of the displacement with respect to that measure. Is that okay? And if it is ergodic, by the ergodic theorem, it is the same as the limit, the average rotation for almost every point. Okay, for typical points, that is true. So every ergodic orbit detects one rotation vector. And I will say that the rotation set is the whole set of rotation vectors for f invariant measures, which is equivalent to taking the convex hull of the ergodic rotation set. Okay, so basically you have all your ergodic measures. For each of them you have a rotation vector. You take that collection, then you take your convex hull. And that's your rotation set. Okay? I will give 3 quick examples to illustrate this. So if you have a linear flow, so everybody's flowing, no singularities, then your rotation set will be a point, because everybody's doing the same thing. Is that okay? So the rotation set of the time one map of a linear flow is a point. So a little bit more difficult. This is a point push. What's a point push? Essentially, what I drew there is the anisotropy, a path from the identity to my function f. So I have the identity, and I basically have my torus, and I squeeze and twist. That's the idea. Twist is a tricky word. This is isotopic to the identity. So let me draw only one thing. If you have the image of the horizontal curve, this one, would be something like this. It comes here, then it goes up, and then it comes back. So the isotopic classes are preserved. The homotopic classes are preserved, okay? But I have some kind of, it's called point push. And if you look there, in the boundaries of the strip I took, it is the identity. In the middle, it is like one whole loop, and then I interpolate, okay? So it decreases. So for this case, the rotation set is a segment. I have ergodic measures rotating nothing. I have ergodic measures rotating 1 upstairs, and everything in the middle. So what happens if I compose 2 of them? I will get a rotation set with an empty interior. So in blue, you have a point push. In orange, you have another point push. So if you choose the loops correctly, let's say integer in the middle and in the middle, integer amount of loops, then you will have points which go like this, points going like this in the universal covering, I mean like this and like this, and one point in the cross going like this, you know, so this, this, and this. So you will get a rotation set, something like a square, because you have this, you have this, you have this, you also have 0. So all this will be contained in your rotation set. Okay? So the dynamics of that looks something, in some sense, something like this. Are there any questions? Is everything clear? Okay. Okay, I have to use one more slide to give some quick notions, so that I can state the statement. Okay. So, okay, horseshoes already appeared yesterday. Thank you, Ana and Lorenzo. So, you know this main classical example, you know, stretch and fold. You have your rectangle, you stretch, you fold, then you have entropy, periodic orbits, everything you like. So this, yeah, yes. If you do something like this, then you're happy, okay? But in our case, we will deal with rotational horseshoes. So in our case, instead of stretch and fold, we will do stretch and wrap, okay? So it is essentially the same thing. Let me just draw it. So you can do this in any surface, but I will take the torus. So imagine you have your rectangle, so like this. And imagine that the iterate goes something like this. Something like this. So it intersects twice in a Markovian way, which is what you're seeing in the drawing. But what you have now is that the orbits, I mean the zeros and the ones, if you want, codify the rotation. You know, if I have all ones, it says that I'm rotating. If I have 0, 1, 0, 1, okay, so speed 1/2. And I can do this however I want. I can do this more convoluted. So I'm sorry, these ones should be blue. Okay? What's it? It goes behind.
Okay. So in our two, it's there are two different squares.
Yeah, thank you. Exactly. So something like, I will for sure mess with the colors, but like this, I would say. Okay? Or the other way around, it's okay. Is that okay? So essentially the horseshoe, but with rotational information. So two quick things. The dynamical diameter of a continuum in the torus will be the supremum of the diameter of every iterate of its orbit. And let me clarify, I am measuring the diameter in the universal covering. Okay? So you take inessential continue. So essentially contractible continue. So what I'm saying is, I have the torus, and if I have, for example, this guy is really long, okay? Because what I do is I lift. I go to the universal covering, and it will look like this, so long, okay? And I will say, so this is a technical definition, I will say that F is infinitely continuum-wise expansive if every non-trivial continuum has dynamical diameter equal to infinity, I don't know. So what I'm saying is that every non-trivial continuum, when you start to iterate in it, the supremums go to infinity. So it basically stretches. You may very well think as pieces of stable or unstable manifolds. Okay? Questions? Statement. Okay? So remember, isotopic to the identity homeomorphisms, non-empty interior for the rotation set. We show that F, the original one, is an extension of a map with better understood dynamics and with the same rotation set. Okay? So theorem, this was done by Andrés Carvalho, Andrés, and Fabio for the C1 plus alpha class, and in a joint work with Fabio for the C0 class. So again, hypothesis. Then there exists a factor G, which is also an isotopic to the identity homomorphism of the torus by a monotone semiconjugacy. So monotone means that the fibers are connected, okay? So we are basically collapsing things. In your heads, you can very well think that we are collapsing the islands, okay? We are not, but kind of, okay? So imagine that I have that, and what I basically do is, okay, so this, I will say that there is only 1 point, and this is 1 point, and this is 1 point, okay? Because all the islands, all the points go together, you know? They don't separate. So let me be more precise. What do I get in the result? So same rotation set for the quotient. Infinitely continuum-wise expansive. So I stretch everything infinitely. Tight. Okay, so every non-trivial continuum carries positive entropy. Mixing, topologically mixing. Then set of horseshoes. Nice. What does this mean? Then set of horseshoes, what I mean by this is, then set of rotational horseshoes, actually. I'm sorry. So you take your favorite open set in the torus, small, if you want, and inside here, you will have something like this, everywhere. Okay? So here you will have a horseshoe, here you will have a horseshoe, and so on. So fully chaotic. Chaos is everywhere. And it's also area preserving. So amazing. You know, that is actually a consequence from the fifth one. Okay, it preserves a full support atomless measure. So up to a change of coordinates, it is the Lebesgue measure. So you can very well think it is area preserving. Consequences. So a convex compact subset of R2 with non-empty interior is realized as a rotation set of the homomorphism only if it is realized as a rotation set of an area preserving homomorphism. What is this that I'm saying here? There's a question for rotation sets, which is this set realized as a rotation set of a homomorphism? So what we're saying is, it is only if it is realized by something which is area preserving. So smaller family to look in. This question is quite open, I would say. There are some examples, but some quirky examples. But for instance, there are no known examples where the rotation set has uncountably many extremal points. So for example, the unitary disk. Okay, polygons, yeah. Stranger things, I wouldn't say so. Questions? So let me give 2 more corollaries and then just an outline of the proof. Another corollary, if this homomorphism is transitive, and again rotation set with non-empty interior, then you get it is mixing. And if 0 belongs to the interior of the rotation set of the lift, then the lift is also mixing. So not only you're mixing, but you're also mixing in the lift, meaning that you will intersect any 2 open sets, but looping however you like before intersecting. And another corollary, bounded diameter of elliptic islands. Remember that we were talking about the size of the islands. So they are actually uniformly bounded, okay? If we are in the context of the standard map, then the diameter of the elliptic islands is actually uniformly bounded. So they are like well behaved. Both of these had been obtained by Salvador Sanata in the C1 plus alpha class, again based in theory. So the improvement here would be taking that hypothesis out and only using topological methods. Questions? How much time do I have? 4 minutes? 3.5? Perfect. So outline, it's basically 3 slides. So 3 steps, okay? I want to collapse, remember. The idea is not, it is more or less to collapse the islands. What we will do is to collapse points which belong to a continuum which is dynamically bounded. So let me say this. Imagine that I have this continuum. Okay, so let's think of an island. All of these points, the island is periodic. So when I iterate, it goes like this, then this, then this, and then comes back. So if I look at the dynamical diameter, it is uniformly bounded, okay, because it's 4 numbers. So all those points will accompany each other. So I don't care. I kill it, okay? The idea is, okay, we say 2 points are equivalent if there exists a continuum containing both with finite dynamical diameter. And the main proposition, I cannot emphasize this enough, that is the main proposition, is that there exists a uniform bound. What I'm saying is, if something is big, it explodes. Again, if something is big, it must go to infinity in size. Okay, with that proposition, we obtain a partition of the torus into an essential field continua. So for example, the green one is a class, the red one, sorry, this is one class, this is one class, this is one class, this is one class, this is another class, this is another class, this is another class. And the equivalence relation is super semi-continuous, meaning that the Hausdorff limit of classes is contained in a class. For example, if I have class, 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 then I might go to class, thick class. Sorry. But it is important that all these points belong to the same class. Okay? So Hausdorff limit of classes is contained in a class. Then by a result of Moore or Robert Senroth, whoever you prefer, the quotient is a homomorphic surface. Okay? So you're essentially taking some blobs, collapse, 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 same surface. Okay, we substitute, as I said, Bayesian theory for topological methods, being Brouwer, Le Calvé, Sekevar foliation, and forcing theory by Patrice and Fabio. Okay, first step, quicker. Second step, you have to look at the quotient dynamics for several weeks or months or, I don't know, for a lot of time with focus. And some easy consequences will appear. So same rotation set looks easy, you know, because you collapsed things which stay together. So the linear drifts to infinity are the same. Okay, so same rotation set. Infinitely continuum-wise expansive is also easy, because when you're in the quotient, ugly torus for the quotient, if you take a continuum and you look at the per image, you're intersecting several classes. And if you're intersecting several classes, you will grow to infinity. And infinity here means infinity here, because what you're collapsing is uniformly bounded, okay? So those are, I would say, the easiest. You can also obtain tight. Let me check if it is this. You can also obtain tight, only checking that it is continuum-wise expansive. And with the first 2 properties, you can build the whole rest, 4, 5, and 6. Essentially 5, which is this. So rotational horseshoes. This is a little bit of a technical part. The idea is that in the quotient, every point will have a non-trivial stable set and a non-trivial unstable set. And what you do is, in the spirit of the lambda lemma, you want to build heteroclinic intersections. Okay? You might know, maybe you know this drawing. If you have a hyperbolic fixed point and something like this, homoclinic intersection, then this implies a horseshoe. You draw a rectangle here, and exercise show that an iterate of that does a horseshoe. So we build something like that, something like rectangles, except that the boundaries are not sides, but continua. And we prove that each of them contains a horseshoe, unique homoclinic class. And with that, you can prove that you preserve a full support Hudson-Blais measure, which is conjugate to the Lebesgue measure, and that's all. No, work in progress, blah, 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 higher genus, blah, blah. Thank you very much.
Okay.